So here we're going to be talking about midsegments and the midsegment theorem. So a midsegment joins the midpoints of two sides of a triangle. So we have these two sides connecting their midpoints creates one midsegment. I have these two sides connecting their midpoints creates another midsegment, and then connecting these two sides, their midpoints, creates a third midsegment. So each triangle has three midsegments, and the midsegment theorem says that those midsegments are parallel and half the length of the third side. So this, actually using these markings, this length is the same as that length because that's half of this side, and this is parallel to that. This one is parallel to that and congruent to half of that length. And this midsegment is parallel to that third side and congruent to half of its length. Alright, so here we are going to prove the midsegment theorem, which actually says two different things. Both that MN is parallel to DE and that MN is half the length of DE. So let's take this one at a time. Let's actually try to prove the parallel part first. So I'm going to try to prove that this is parallel to that. And the first thing I'm going to do is take this triangle DEF with these 3 points as its vertices. So that is just my given statement. I'm going to first find the slope of line DE. So DE slope is y2 minus y1, so 0 minus 0 over a minus 0, x2 minus x1, which is just 0 over a, which is 0. Here we're just applying the slope formula. I'm going to call that the application of the slope formula. And that's to show that this line has a slope of 0. And remember, this is just an arbitrary triangle where we have these variable coordinates. This just happens to be set along the x-axis, but this is just an arbitrary random triangle to show that this actually will work for any triangle. So I set this along the x-axis, giving that a slope of 0. Now I'm going to prove that this also has a slope of 0. So to get the slope of that line, I'm going to need the coordinates of that line. And I know that M is the midpoint of that line, and N is the midpoint of that line. So I'm going to apply the midpoint formula twice. I'm going to say that B plus 0 divided by 2 is the x-coordinate, and C plus 0 is the y-coordinate for point M, and then N is these two. So B plus A divided by 2 is the x-coordinate, and C plus 0 divided by 2 is the y-coordinate. So this, actually, I'm going to simplify these. C plus 0 is just C, and B plus 0 is just B. That's B over 2. That one's C over 2, and this one's also C over 2. So both of these are the application of the midpoint formula. Just showing those two midpoints. And now I'm going to apply the slope formula again. To find the slope between points MN. So I'm going to do C over 2 minus C over 2, y2 minus y1. And then actually let's think about N as my y 2, and x2, so that I can just subtract in that order. B plus A over 2 minus B over 2. That simplifies to 0 over A over 2, but really doesn't matter. 0 over anything is just 0. So those two lines have the same slope. And by the parallel lines theorem, DE is parallel to MN because they have the same slope. So actually for the next part, I'm going to steal some steps that I used in here. So to prove that MN is half the length of DE, I don't really need the slope here anymore. So I'm going to get rid of that. But I know I'm going to need the coordinates for my vertices, and I'm going to need the coordinates for M and N. So I'm actually going to steal steps 3 and 4 and just slide them up. So I'm going to use those for steps 2 and 3. And I guess actually I missed this part of my given statement, that I should have said that in my first proof also, but that is going to be a part of my given statement for statement 1, that is also the midpoint of DF, and N is the midpoint of FE, just so I can actually apply the midpoint formula to show those coordinates. So from here, I'm going to apply the distance formula to find the distance of length DE. So that is the square root of y2 minus y1 squared. So that's 0 minus 0 squared plus x2 minus x1 a minus 0 also squared. So I'm actually just going to do the simplifying inside of there. 0 minus 0 squared, that's just going to be 0, so that's going to completely go away. And then a minus 0 squared, that's going to be a squared. So I'm taking the square root of a squared, which is just a. So now I'm going to find the length of MN the exact same way using the distance formula. So that's the square root of these two subtracted, c over 2 minus c over 2 squared, and these two subtracted, b plus a over 2 minus b over 2 squared. So I'm going to do the simplifying in there again. C over 2 minus c over 2 squared, that's 0 squared. That's going to disappear again. And inside of this set of parentheses, I can subtract what's on top there. The b and b would cancel out, and that would give me a over 2 in parentheses squared. And then I'm going to, actually I'm just going to apply the square root right now. If I'm squaring this and square rooting that, that's going to completely cancel out. You can also distribute the squared. That would give you a squared over 4, and then do the square root of the top and the bottom separately. But that's going to give us the exact same thing. The squared and square root process completely cancel out and leaves us with a over 2. And so since MN equals a over 2 and DE equals a, by substituting that in, I'm showing that I have length MN, that's half of length DE.